Okay, can you guys see my screen right now? I think you can. Okay, nice. All right, so let's start. So the material I prepare for my talk is mainly cyclic groups. Also, we talk about coset leading to a proof to the Lagrange theorem. Okay, so the main reference is this AATA book. Is free. It's online. Okay, this is a pretty nice abstract algebra that does not go too deep, so I use that as a reference. Okay, and let's start with isomorphism. So in ZK and cryptography in general, we don't care about homomorphism. We only care about isomorphism. Okay, so there's a theory on homomorphism. We are not going to cover that. We're gonna focus on the isomorphic stuff. Okay, so the definition, we have two groups. One is the set is G, binary operator is the dot. The other is set H with a binary operator circle. So they are isomorphic if there exists a bijection. So bijective mapping means it is both injective and surjective. We call that mapping phi, and it is from G to H. So it has to satisfy the homomorphism definition, which is phi of A times B. Pay attention to this times. So this is a operation in the first group and equals phi A circle phi B, which is the operation in the second group. So they are different, okay? And so a good way to memorize this is consider this is you do the operation first and then do the map. On the right hand side is you do the map first and then do the operation. So it's like a it's like a flip order symmetry stuff. Okay. So this part is the homomorphism definition. Together, it has to satisfy the bijection requirement, which you have to show this function phi is both surjective and injective to prove that it is bijective. So combining these two requirements, you have a isomorphism. Okay. So that is the definition. Let's work through an example. The example I picked is Z-mod for Z is isomorphic to the cyclic group generated by I. This I is just that famous I in complex numbers. Okay, so I square equals -1. That I. Okay, so the definition is we set phi as a function from Z-mod for Z to that cyclic group generated by I. So this pointy bracket means cyclic group generated by this element. Okay. So the I think this is wrong. I should put colon here, but whatever. So the definition of the map is we map n to I to the n power. So why does it work? Because we can find a one-to-one correspondence by mapping each element to that element in the other group. For example, map 0 to I to 0 power, you got 1, okay? Map 1 to I to the 1, you got I. Map 2 to the I to 2, you got -1. And map 3 to I to the third, you got -I. So you see this, we can generate, no, I mean, we can map to every element on the other group, okay? So we cover everything. So that group only contains 4 elements. So plus minus 1 and plus minus I, okay? You can see the homomorphism requirement is satisfied because we can break it down to I to the n plus n, and these m and n are just, I mean, they are in Z-mod for Z. And you can break down that exponentiation into a product I to the m times I to the n, and further convert them back to phi m times phi n, so it satisfies the requirement here. Okay, so the dot here is just plus, the circle here is multiplication, so they are different operations. Okay, so personally I like visualizing this thing in a circle, so you can see yeah, kind of like we map 0 to I to 0. Okay, so this is like the visualization of the one-to-one correspondence. Okay, we don't need to prove bijectivity here because we can find a one-to-one correspondence. Like we literally map every element here, so we found everything. We don't have to prove it. So this is the bijection. This is the homomorphic requirement. Okay. Do we have questions so far? No questions. I'm gonna continue. Yeah, this is pretty easy for you guys, I think. So a theorem, phi be a isomorphism, then inverse phi. The inverse mapping is isomorphism also. Okay. So because it is isomorphism, and the number of elements in G equals to the number of elements in H, because there is one-to-one correspondence between them. This is pretty easy to understand. Okay, so abelian property transfers to the other group because they are isomorphism. If G is abelian, then H is abelian. If G is cyclic, then H is cyclic. So basically, they are kind of like the same, but they are not the strict same, but they are considered the same in mathematical scenario. Okay. So basically, you can think of isomorphism as the group G is equal to the group H. Yeah, kind of. Okay. Also has a property saying if G has a subgroup of order n, then H has that same subgroup of order n. Okay. And so this theorem basically says the properties transfer to the other group. Okay. Here's a important theorem, says if G is a cyclic group of infinite order, then it is isomorphic to the integers. Okay, so G can be anything. So any cyclic group of infinite order is isomorphic to the integers. Any cyclic group of order n, so finite order, it is a finite cyclic order. It is a finite cyclic group of order n. Then it is isomorphic to Z mod Z. And a special case of that is if you have a prime order group, then it is isomorphic to Z mod PZ. So why we don't mention it is a cyclic group of order P? Because there's a theorem. This is the corollary of Lagrange theorem, saying if you have a group of order P, then it is cyclic. And every non-element, so I mean G not equal to E. So any non-identity element is the generator. Okay. So basically, there are P-1 generators. So this we are not going to talk about it now. We're gonna talk about it in the end of this talk. Okay. So how do you visualize this? I think for the first statement, I like think of these two number lines. Okay. So I put Z on the bottom. So Z is like an infinite number line. Okay. So I map 0 to A to 0. I map 1 to A to 1, so on and so forth, okay? So this is the first case. You can see we kind of construct one-to-one correspondence here, but we are not going to prove it formally, okay? So any cyclic group of infinite order, visualize it as a number line, infinite number line, okay? Is isomorphic to Z because we can find one-to-one correspondence. For second statement, any cyclic group of finite order, I like to visualize that as a clock, as a circle. You can see this is a cyclic group. You multiply A continuously, and then it gets back to A0. So this is the identity element, okay? You go back to A to 0 in the end. And you can map that finite amount of numbers, Z mod n Z, which contains elements from 0 to n minus 1. You can map them to each dot on the clock. Kind of construct one-to-one correspondence, okay? So they are isomorphic. So more formally, you have to prove this phi maps n from A to the n, and this k to A to the k. You have to prove the homomorphic requirement, also have to show this is a bijection, okay? And this third statement is just a special case of the second. So this is the consequence of Lagrange theorem. Maybe you want to memorize all three, okay? So you can see kind of Z mod n Z, Z mod PZ, they are the only special groups. I mean, if we study enough theory on Z mod n Z, Z mod PZ, we can apply the same theory to any other cyclic group because they are isomorphic. Their properties transfer, okay? So if we study enough theory on these three groups, we can apply the same thing to other cyclic groups. So that's why these examples are important and we study them a lot, okay? Okay, that's for isomorphism. Do we have questions so far? No questions. No questions. Okay, let's continue. So we studied isomorphism. Right now we are moving to more cyclic group theory. We covered what is cyclic group last week, right? So remind you that it is visualized as a clock, okay? So oftentimes a subgroup will depend entirely on a single element of the group, okay? So this is the motivation. How do I know this? Take a few examples. For example, 3Z is the set, okay? You can say it is generated by 3, keep adding 3, so you move to the right. Or you can say generated by -3, you start from the right and subtract 3 to get to the left, okay? So this one is a cyclic subgroup of Z, okay? And the generator is 3 or -3, okay? So another example is H, which contains 2 to the nth power and is an integer. The binary operator is multiplication here, okay? So we expand that set a bit. We see the identity 1. This is 2 to the 0, 2 to the 1, 2 to the 2. Or to the left, this is 2 to the -1, -2, okay? So the generator is either you multiply 2 to get from left to right, or you multiply inverse of 2 to get from right to the left. So this set is a cyclic subgroup of the rational numbers under multiplication. Okay. We cover two examples of cyclic subgroup. Next is what is this? Okay, so this is I think this theorem says how do we construct a cyclic subgroup? Okay. So we use this notation pointy bracket A. This is this refers to a to the kth power, where k is an integer. Suppose this is under multiplication, okay? And we take any element A and we write down the powers of A. This is a subgroup of G. And also this is the smallest subgroup of G that contains A, okay? Basically, this is just saying how to construct a cyclic subgroup from a normal group. So you can pick any element from it and then write down the powers. Okay. Yeah. If the binary operator is plus, then you just say n times a instead of a to the k power. Okay. And here's a formal definition of that. So if this pointy bracket A equals the entire group G, then G is a cyclic group generated by A. We call A the generator. Okay. But that's not always the case, because usually this pointy bracket A will be a subset of the group. So if that happens to be the entire group, then the group G is a cyclic group. Otherwise, this is just a cyclic subgroup. Okay. Okay, so this is the definition of order of an element. So for any, pay attention, we are not talking about the order of A in a cyclic group. We are talking about in general group might not be cyclic, okay? So the order of A is the smallest positive integer such that n to the a to the nth power is the identity. Maybe such n exists, so the group is no. I mean, if that n exists, then A has a finite order, and we denote that as this A bar, A modulus, A absolute value, whatever, equals n. Okay. Otherwise, we say the order of the element is infinity. So this is pretty easy to understand why we say the smallest positive integer, because you can have many things maps to E, because you have A to the n equals the identity. Also, you can square that. Well, third power is still E. Okay, so for the order, we only care about the non-trivial one, which is the smallest. So this one. Okay. Questions so far? Oh, no question. You guys are pretty quiet today. No questions, right? Okay, let's continue. I have to emphasize again that the definition we talk about isn't for a cyclic group. We are talking about for general group, a group G that might not be cyclic. Some element A in that probably have order. Okay, probably. The other case is just it does not have that order, so it's infinite order. Okay. Example, I think we covered this last week. Cyclic group can have more than one generator. So for Zima 6Z, it can be generated by 1. So +1 +1 +1. you reach to all the elements here, or you can generate that by 5, okay? So both of them are generators, okay? Generator is not unique. Also, not every element is generator. For example, 2 is not a generator because it only covers 0, 2, and 4, which is not ZMOD 6Z, and it is only a subset of that, okay? So 2 is not a generator. Generator can be 1 or 5. Generator is not unique. Generator is not, like not every element will be a generator, okay? For Z and ZMOD and Z case, I think I should say or here, you know, this. Yeah, I think, oh, wait. Yeah, this is or. Yeah, I'll fix that later. So generator of Z, which is an infinite cyclic group, you either use generator 1 to go from left to right, you keep adding 1, or keep subtracting 1 to go from right to left, okay? I think this is or. Yeah. And generator for ZMOD NZ can be 1. As you see, 1 literally can generate any ZMOD NZ group, but some other element can also generate that. So 1 is not the only generator. It has some other element, but it depends on the case, okay? So it's a case by case. Famous theorem saying, very famous one, probably you should memorize this, is if a group G is cyclic, then it is abelian, but not the reverse. So if a group G is abelian, it doesn't have to be cyclic, but if it's cyclic, it has to be abelian. So how to prove that? I got this idea from ZK book, okay? So the basic idea is just you pick some, for example, saying we work with addition, okay? So pick some element R, because it's a cyclic group, it can be represented by P plus Q. So P is A, keep adding A for X times, and Q is keep adding A for Y times. So P plus Q, or it can be represented as Q plus P. So you just flip the order here. First you add A for Y times, then you add A for X times. So this is kind of the abelian thing, okay? So it's not a formal proof, but I think it's easier to understand this way. So I include here. So this is the idea. You just break down things, or you can do multiplication here. It doesn't matter. Okay. So the idea is still the same. Theorem: every subgroup of cyclic group is cyclic. This one is pretty easy to remember. Okay. A corollary of that is the subgroups of Z are just NZ. So 2Z, 3Z, 4Z, so on and so forth. Okay. Z is cyclic. Also, the subgroups NZ are also cyclic. And coming next. Oh wait, do we have questions so far? Need to be co-prime. Wait, which one? Which one need to be co-prime? Co-prime. I don't think so. Are you talking about this theorem? No, I don't think we are using far back to be generator of G. Okay. So what's the condition for a generator Oh, yes, yes, yes. I think you are right. Yes. That's a I think that's the consequence of Lagrange theorem, right? So yeah, I think so. Coprime for Melio theorem or that. Yeah, I remember something. Or probably I will cover that somewhere. I don't remember. Generator. Yeah, I think so. Yes. If an element, for example, in Z mod NZ, if an element is coprime to the modulus n, then it is a generator. I think we talked about this last week in the Euler phi function, somewhere around there. Okay. Yeah. So for Z mod PZ, every element is coprime with P. Therefore, everything there other than 0 is the generator. Yeah. Okay. And let's continue. Oh, this is a pretty fun one. Proposition. Suppose a group G is cyclic with order n. Okay. It is generated by A. Then I claim that A to the kth power is the identity if and only if n divides k. I think this is pretty obvious. So why is it obvious? And you have A to the n equals E. Also, you can square that or keep adding A to the n to this expression. Okay, you can keep on going. You will have n divides k. So k here is k equals n, k equals 2n, k equals 3n. K is always a factor of that. Okay, so this proposition just saying you have multiple, you can have many infinite things that equals E, but they are some multiples of I mean some exponential of A to the n. Okay. So this proposition, keep in mind, we are going to use it soon. So a very important theorem, I think this one is most people don't understand when they take a first course in group theory. Okay, so this one was pretty confusing to me. I just skipped the proof. Now I come back, I understand the proof. So G, let G be a cyclic group with order n. So same setup. G generated by A, same setup. Okay. So I claim that the order of A to the K is n over GCD Kn. So how does it work? So why do we care about the order of A to the K? Because this is some element in the cyclic group, because recall that cyclic group is like a clock, it's like a circle. Everything is some power of the generator. Okay, so generator generates everything. A to the K is some element on the clock. So I claim that the order of the some random element on that is n over GCD of K and n. So yes, the proof is very interesting. Let me show you the proof. So our goal is to find the smallest integer m. The smallest integer m comes from the definition of the order of some element. Okay. So this m basically is just the order of A to the K. That's what we want to show. Okay. So we are looking for this order. We call this order m. That's equivalent to saying A to the K to the M equals to E. That's just the definition of order, okay? So this is A to the K times I, k times m equals e. Okay, so by the proposition above, this one, the order m is the smallest integer such that n divides k times m. Why? Because a to the k equals to e if and only if n divides by k. Okay, so we are working with a to the k times m. So just substitute k times m for k here. You will have if and only if n divides k times m. Okay, so they are equivalent. So this result directly comes from this proposition. We are using this proposition to prove this theorem. Okay, yeah, we use that here, and then now we have n divides km. So what does it mean? We can divide GCD of k and n on both sides. Okay, so we divide this big chunk of GCD of k and n on both sides. We can factor m out because this is just a definition of that middle school algebra. Okay, we can take m out. So now we are left with two big chunks. So this chunk and this chunk. I claim that they are co-prime. So why are they co-prime? I think it's easier to work through a concrete example. Okay, so consider 12 and 18. The GCD of them is just 6. Okay, so this is 2 times 6 equals 12, and 3 times 6 equals 18. For example, I am dividing this GCD thing on both of them. So 12 divided by 6, 2. 18 divided by 6 is 3. And the result, 2 and 3, are just co-prime. I call this, they are in simplified form, but this is not a formal definition. It is some concept that I created to help myself understand this. Okay. So basically 2 is just this n divided by this GCD big chunk. 3 is here. So they are co-prime. They are co-prime is the same as saying they don't divide each other because they are co-prime. This, I think, is just a definition of co-prime, saying the definition is the only common divisor of them is 1, right? You cannot further divide some divisor out of them concurrently. So their co-prime means this big chunk does not divide the other chunk. So, but this holds, So this was true. Yeah, we have this condition 1, condition 2. We can combine them, saying, oh, so the big chunks, they don't divide each other. So the thing on left hand side must divide m. This must hold, otherwise this equation cannot be true. Yeah, So we are going to from this big chunk, and our conclusion is n over GCD must divide m. This must be true. Okay, so what does it mean is n over GCD is m times some integer. Okay, so this one, so oh no, I mean m equals to n over GCD times some integer. So m will be some multiples of this. Okay, so we are looking for the smallest integer by definition. So what is the smallest integer? It means m equals to that. So just 1 times. So we let the multiple be 1. So this should be the smallest possible integer for m. So we got the answer. M is the order. M is the order. Okay. Yeah, this is a pretty fun proof. Do we have questions on this? Oh, no question. You guys are smart. Yeah, this one, yeah, pretty interesting. Okay. Yeah, the proof here is pretty interesting. Okay. So why I said this theorem is important is because it provides a way of counting the number of generators in a finite cyclic group. So how does it work? Let's say this theorem implies this corollary, okay? So same setup, G equals to generated by 1 is a group, cyclic group generated by 1 of order n, okay? So then a to the k, I remind you, is an element in the cyclic group because it is a clock. Everything is some power of the generator. It is so a to the k. A to the k is a generator if and only if GCD of k n equals 1. Oh, okay. I think I answered the question just now. Okay. Yeah. Yeah, we were talking about this. Okay, so the only condition for a to the k being a generator is the power has to be co-prime to n. Yeah, I think we worked this last week for Zima and Z, right? We followed the Euler phi function and we proved this in Zima and Z. And right now it is we are showing this result can be generalized to this one. So this is for a general cyclic group. So not only Zima and Z. But you should know that any group with order n, cyclic group with order n, it is isomorphic to Zima and Z. So those results are related. Yeah, they are the same thing. Okay. Yeah, the number of generators is just phi of n. We talked about this last week. Okay. Yeah, sometimes this is confusing. There are many theorems you should memorize, but yeah, you can just remember that such group is always isomorphic to Zima and Z. So you prove this in Zima and Z, and then you can say this result works for such cyclic groups in general. Okay. In the end, we take an example, Zima 16Z. The coprime elements from it is 1, 3, 5, 7, 9, 11, 13, 15. Okay, they are all generators. So why you should check them one by one, but for simplicity, we are saying just take 9. Like you can multiply 9 with every element from Zima 16Z, and you can see that it generates every element in modulo 16. Okay, and you should check for all other generators, but it's waste of time, so we are not going to do it here. Okay, questions so far? No questions. Nice. And the other important thing before I show you Lagrange theorem is the coset. This is also a pretty confusing concept for a first course in group theory, so we cover it here. Definition, left coset, it is G to capital H, G times capital H. So this one is the left coset with representative G, and so this set contains every element of the form G times H, where H is any element from the subgroup. Okay, so this H is a subgroup of G. you just multiply G on the left to every element in H. That's pretty much what it is, okay? So there is also a concept called right coset. As you can imagine, is you multiply G on the right. So this is GH, this is HG. Same thing, you just multiply a single element. Yet remember, this representative is you pick a single element from the group. It's not from the subgroup. You pick any element from the group, and then you multiply that to every element in the subgroup. This is what a coset means, okay? So for a concrete example, let's say, for example, H equals to 0 and 3. This is a subgroup of Z mod 6Z. And all the, I should say, left cosets here, okay? So all the left cosets of H with representative, no. I mean, all the left cosets of H are the following. So Z plus H equals 3 plus H. Why? Because it is Z and 0 and 3. This one is 3 and 6, and 6 mod 6 is 0. So 0, 3, 3, 0, 1, 4, 4, 1, 2, 5, 5, 2. You can see the symmetry here, okay? So there are only 3 cosets, although there are 6 elements, because like 2 of them are equivalent. So 0 plus H equivalent to 3 plus H, because you can do the arithmetic here. Okay, so there are only 3 distinct cosets here, left cosets. And also a comment here is saying, since this Z mod 6Z under addition is commutative, so left cosets are just right cosets, because 3 plus H equals to H plus 3, so everything is a billion, okay? Here's a lemma. So this is pretty just like a tool for the proof. So they are pretty easy to prove. So I'm not going to do it. And the idea is saying the following are equivalent. What does it mean is, if one of them is true, then you can derive for the others. So it doesn't mean all the followings are true, It's just saying that all the followings are equivalent. You have to make one statement true for the others to hold. So usually we care about proving G1H equals to G2H. So I box it here so I can pay attention. Okay. Followings are equivalent. Doesn't mean following are true always. Okay. So a important theorem saying if H is an subgroup of G, then left cosets of H in G partition G. Okay. Or the left cosets of H partition G. What does it mean is G will be a disjoint union of left cosets of H. So that's pretty hard to understand, but we can visualize it. Okay. So personally, I like to visualize this as a chocolate bar. So for example, we have a group contains 6 elements G1 to G6. We can visualize the left cosets G1H, G2H, all of them just partition the group. So basically it looks like a chocolate bar, okay? And there's a theorem saying the size of each coset is equal to the size of the subgroup. I'm not going to prove that. You can find the proof online easily, okay? So basically, you have to show this first. You have to show that the size of the coset equals to the size of the subgroup, and then you know that different cosets of the same subgroup, they must have equal size. Okay, so this G is you can pick any G. You can pick like G1 to G6 as you wish. So all of the cosets have equal size. So it is pretty obvious that you can visualize as a chocolate bar with the same size. Okay, so this one is pretty nice tool I use to remember these theorems. So we do a quick proof on the theorem itself. So our goal is to prove that all the left cosets partition G. Easier way to do that is to prove all the left cosets are disjoint union. So without loss of generality, we say G1H and G2H are two cosets. Okay, so we pick two cosets and we do a proof on these two that can be generalized to any pair of cosets here. So this is like we prove a special case, and then you can generalize the proof to every pair. So the proof holds. Okay. So we pick two cosets with a different representative G1 and G2, and we want to show that they are disjoint union. So the definition of disjoint union is just either we have the case that G1H, this coset intersect with G2H, the intersection is empty set. So that means they are disjoint, okay? So, or we can have G1H equals to G2H. So they are equal. I think this, you don't have to prove this, I think, okay? So this one is just, like this case is trivial, so we only focus on the first one. For the sake of contradiction, we want to prove the intersection is the empty set, but it is pretty hard to do that because we don't have like a condition to start with. So for the sake of contradiction, we say the intersection is not empty. So we can pick any random element A from the intersection, then we can kickstart the proof. We pick this element A from the intersection. It implies two things, okay? So the first thing is A is in G1H. The other is A is in G2H. So we have a system of equations. So two equations. The first one corresponds to the left, and the second equation corresponds to the right. Okay? Yeah, because the first coset has all the elements of the form G1 times Leo H. The other have G2 times Leo H. So we can say, oh, we have different elements from H1 and H2. A equals to G1 H1, also A equals to G2 H2. So we can solve the equation and say G1 H1 equals to G2 H2. You can multiply H inverse on the right for both sides. So you have G1 equals G2 parentheses H2 times H1 inverse. The inverse comes from here, okay? Inverse. Recall that by the definition of a group, the inverse, of course, is in the group. That's the definition, okay? The inverse is in the group. H2 is in the group by definition also. Okay, so we multiply them. They should be in the group by closure. So H2 times H1 inverse is in the group of H. So we can say, because this long thing is in H, so it equals to G1. So G1 has to be in no, I mean, because H2 times H1 inverse is in H, so G2 times that must be G2 capital H, okay? So because G1 equals to that, so G1 is also in the coset, okay? And by the lemma above, like this lemma, we have 4 implies 1. Because of the symmetry, this says G2 is in G1H. You can derive that into G1 is in G2H. So 4 implies 1. 4 implies 1 is what we use here. Okay? So that proves that left coset partition G. So again, I think the takeaway from this is just visualize this as a chocolate bar. This is the thing I invent. This is pretty smart, I think. Okay. Yeah. Yeah, just visualize left coset as this chocolate bar. So everything has equal size and they partition the entire group. Okay. So this is the mental picture you should have. A little bit extension. Usually you see this in the textbook, so I had to mention it. It is the index. So bracket G colon H. This notation is the index. H means the number of distinct left cosets of H in G. Okay. So take a concrete example here. Is a Z mod 6Z. We just work out. Okay. So we just work out this example. Index is 3. Why is that? Because they overlap, and they overlap. There are so-called 6 cosets, but they overlap, so they are equivalent. So the distinct number of distinct left cosets are just 3. So the index is 3. Okay. Do we have questions so far? No question. Nice. Okay, we are pretty close to the end. I'm pretty tired. This is long. So the last page, I want to introduce you to Lagrange theorem. This one is definitely the one you should memorize. Okay, so this is the most important theorem we discussed today. It says let H be a subgroup of G, then the order of H divides the order of G. So this means the size or the number of elements in H divides the size or the number of elements in G. So how large is the ratio and size of G over size of H is just the index we just talked about here. Okay, this G colon H is the index. So the ratio between those two is just the number of distinct left cosets. Okay, so a corollary it is okay. Yeah, this one is pretty general because it says for any finite group G, you pick an element from G, then the order of the element must divide the size or the number of elements in G. So you can say that because it is a finite group. Of course, if it is an infinite group, then order will be infinity, I think, right? So this is pretty general, okay? The order of G divides the number of elements in G. I think this, I didn't find a proof of it, okay? But I think the idea of proving it is just think of G as a generator of some cyclic subgroup, because you can always construct a cyclic subgroup, okay? So that pointy bracket G thing, like the G thing. So this thing does not have to cover the entire group. It can be just like a cyclic subgroup. So the elements will be like G to the kth power, okay? it can be just like a small subgroup in the group. We consider this cyclic subgroup generated by G, and we apply Lagrange theorem on it. So since it is a cyclic subgroup, therefore it is a subgroup of G. The order of this subgroup must divide the order of G, the big G, I mean. Okay, so recall that the order of the generator is just the size of the cyclic subgroup, I think, right? Because, for example, if I have G to the third equals to E, then all the elements here will be E, G, G to the 2, and G to the 3. No, there is no G to the 3 because I said G to 3 is E, so I only have 3 elements in the subgroup. So the identity G itself and G squared is the only 3 elements in this subgroup. Okay. So the order of the generator is just the size of the cyclic subgroup I constructed, and by Lagrange, that number had to divide the order of the entire group. So I think that proves this statement. Yeah, maybe confusing, but I think, yeah, that's the idea. Okay. Another important corollary, just following this. So once we prove this one, we can derive this statement saying, oh, we have a finite group of order P, which is a prime, and then G must be cyclic. So this one is pretty important. You should memorize that, right? So any finite order, no, I mean any finite group of order P, it must be cyclic, and anything in it, so every element other than the identity in it is a generator. This will be used in elliptic curves or finite field a lot, so please remember this, okay? And so for a more thorough explanation, I have that in my article. Okay, so this is my personal blog. If you are interested in the proofs, the ideas like how it is used in ECC attacks, please just read my article. This is pretty clear than what I can talk about right now. Okay, so that's the content for today's talk. That's everything. Do we have questions? Otherwise, we can stop today. That's everything. Okay, so no questions? You are welcome. Okay, let's stop for today then, if there's no question. That's all the content. Okay. Wow, that's another hour and a half. That's pretty long. Okay. Nice. I think I will stop sharing and see you guys next week.